Hey everyone, this is Dr. Walker. In this video, we're going to go over example v573, finding the magnetic field of a current-carrying wire. In this example, we have a wire of finite length. It carries a current I, and it's placed along the x-axis. We're trying to find the magnitude of the magnetic field at a point P, which lies a distance a above the origin. So I'm going to go ahead and redraw the wire here. You'll see why in just a second, just so it doesn't get too messy. And it does have a finite length, and notice that the point P is not above the midpoint, so these sides are not the same length on either side. We have a length A right here, and so we know that we can use the Biot-Savart law to find a magnetic field at this point. Let's go ahead and write down the Biot-Savart law. dB is equal to mu naught over 4 pi I ds cross r hat over r squared. We know that the first step is to draw the length element ds that points in the same direction as the current. So let's assume the current is flowing to the right. It doesn't matter in this case because we're only finding the magnitude of the field, but the direction of the current will affect the direction of the magnetic field. So we're going to draw an element ds, a length element, right, that points in the same direction as the current but has a length ds. That's the first step. The second step is to draw the unit vector r hat, which points from the length element ds to the point. Let's draw a little dashed line here. And so r hat is going to point towards that point P over here. Let's go ahead and define an angle between the two. Let's call it phi. Let me write the ds down here so we have more room. And let's call this angle here phi between ds and r. We need this angle because we have to find a cross product between these two vectors. Let's go to the side here and find a cross product, ds cross r. We know that this is going to be equal to ds times 1 times sine of phi. Now, ds is going to be the length of ds, and we can call the length of ds, the length of it, we can call it dx. So this is going to be equal to dx times 1 times sine of phi, which is the angle between ds and r. Now, we can't solve the problem and keep phi in the problem, but we can see that the wire segment here extends from an angle θ1 to an angle θ2. So it's actually going to be more convenient to write the angle up here so that our limits of integration will be relative to the vertical axis here. So let's define theta here between the vertical axis and this line here, which we'll call r, is a distance from the length element to our point P. If that's the case, then we realize that sine of phi is the same as the sine of the little angle over here. You can draw a little angle over here, which would be pi minus phi. The sine of both of these angles is the same. So the last thing, let's call this angle alpha here. So dx sine of alpha, but we want to write it in terms of theta. And if we look at this right triangle here, formed by A and this length, which we can call x, the distance from the origin to our element, just like when we were calculating electric fields due to little charge elements dq's, we defined our distance x here from the origin to that charge element. And so this right triangle formed with A, x, and r, we're looking at this theta here, and then we can see that the sine of phi is going to be equal to, the sine of alpha is going to be equal to the cosine of theta. because we have a right triangle here. Okay, so I know it's a lot of work here, but we're not quite done yet. We're going to want all the variables in terms of theta if they do relate to theta. So we know that dx is related to theta, and we know that r is also related to theta. So let's stay on the side here and rewrite our other variables as well. We can go ahead and first write this one more time just so we can have it simplified a little bit. We're going to have mu naught over 4 pi I dx times cosine of theta for the cross product over r squared. So we need to rewrite dx and r squared in terms of theta. To write dx in terms of theta, let's first look at x. So if we look at our right triangle, we know that the tangent of theta is equal to x over a. So that means that x is equal to a tan of theta. And so if we want dx, then we're going to take the derivative, and that's going to be a secant squared of theta d theta. We can write secant squared of theta as 1 over cosine squared. So this will be our expression here for dx, a d theta over cosine squared of theta. And it's okay to leave it in terms of a, as a does not depend on theta. And let's write r squared as well in terms of theta. We know that if we look at the cosine of theta, it's adjacent over hypotenuse, or a over r. So if cosine is a over r, then r is equal to a over cosine of theta. And then we can just square it for r squared. So now we're ready to plug in all of our expressions in terms of theta. We're going to have mu naught over 4 pi times I times dx, which is a d theta over cosine squared theta times cosine theta divided by r squared. So we're dividing by a squared cosine squared of theta. So a squared divided by cosine squared of theta. All right, just had enough room there. And now we can simplify. This simplifies really well because this cosine squared of theta cancels out this one, and then this a gets canceled out, and we get that dB, go ahead and write it over here, and we're just looking at the magnitude. So the direction, we can said if the current was going to the right, then if we do that cross product of ds cross r, you point your fingers to the right and fold them upwards in the direction of r hat, your thumb is out of the page. So the direction would be in the z direction here, or k direction, but let's just find the magnitude of the field. It's going to be equal to mu naught I over 4 pi, and all we have left here is cosine theta d theta and divided by a over here. So now to find the field, we can just integrate both. Integrate dB, integrate this. Oh, we can just put the integral over here. And what are the limits of integration? Well, if we consider theta to be defined with respect to the y-axis here, and if we define a positive angle as going counterclockwise, then we can say that we're going to integrate from negative theta 1 all the way up to positive theta 2. We're almost done here. I know this is a lot of work. We have, for the field, mu naught I over 4 pi a. The integral of cosine is going to be sine, so we're going to have sine of theta 2 minus sine of negative theta 1. And a sine of a negative angle is the same thing as the negative sine of the positive angle, right? This is equal to negative sine of theta 1. So our final answer is going to be that the magnitude of the magnetic field is going to be equal to mu naught I over 4 pi a times sine of theta 2 plus sine of theta 1. In some places you may find this written a little bit differently, such as sine of theta 1 minus sine of theta 2, and it just depends on how we're defining our angles. Since we took it into account the negative theta 1 in our limits of integration, when we plug in the angles that we are given, we can just plug in positive angles. We've already taken care of the negative sign. Let's go ahead and take a look at part B, which says now calculate the field for the special case of an infinitely long straight wire. So we just found that the magnitude of the field was equal to mu naught over 4 pi I sine of theta 1 plus sine of theta 2 is what we just found. So what if this wire is super long? What are going to be the angles? Well, you can see that the angle gets bigger and bigger the longer the wire is. If the wire is infinitely long, then it's the same as though that point P is really, really close. And you can see that the angle gets closer and closer to pi over 2. So all we have to do to find the field due to an infinitely long straight wire is plug in our theta 1 is equal to pi over 2 and our theta 2 is equal to pi over 2. Remember, we've already taken care of the signs when deriving this equation. Sine of pi over 2 is equal to 1 for both cases. We'll plug in pi over 2, so we're going to get 1 plus 1 over here. So we're going to get the magnitude of the field is equal to mu naught I 2 over 4 pi. So the 2 cancels out. And we get, I feel like I'm missing an A somewhere. Let's go back here. Yep, I was missing an A. Let's go ahead and put that A in here. I knew I was missing something. All right, so it's going to equal to mu naught I over 2 pi A, where A is the distance from the infinitely long wire to that point. It's the perpendicular distance from the wire to that point P. So that is it, and in the next video we're going to actually learn a right-hand rule to find the direction of the field, even though we already can use the Biot-Savart law to find the direction. We said in the previous page, if the current was going to the right, that field would be pointing out of the page. But this is just a magnitude of the field, and let's save the direction for the next video.